Hi everyone, I'm Oliver Church, and thank you for everyone that subscribed after my last video where I talked about a TurboQuant implementation that could improve the context window of local AI workflows. So, you might be wondering what I'm going to be talking about for this video. Most people think you need a $200 a month API subscription just to run AI agents. Well, I'm running 8 of them simultaneously on 2 graphics cards, some managing sprints and running tests on a local model, others orchestrating cloud AI through automated dev loops. Together, they're building real software autonomously. Today, I'm going to show you exactly how I built this, what model I'm using, and why local AI agents might be the most underrated tool in a developer's arsenal right now. Let's talk about why you'd want to run AI agents locally instead of using cloud APIs. So, cloud API costs for agentic workloads can be brutal. An agent that thinks, uses tools, and iterates through a problem can burn through 50 to 100,000 tokens per task. At cloud or GPT-4 pricing, that's $1 to $3 per task. Running 8 agents doing hundreds of tasks adds up to hundreds of dollars per day. My local setup does the same work for the cost of electricity. And one more point I'll make is that the majority of agentic AI tasks do not actually have to be very intelligent. So if you have a lot of tasks that don't require a necessarily large model, such as Claude, then you'll find a local model more than capable, right? So a lot of things like testing, um, like just orchestration tasks, you don't need a cloud model. And think of it like if you have a team of employees, right? You might have one incredibly good software engineer, but then you have a bunch of other employees that don't need to be software engineers. So I think especially for those other tasks, those non-programming tasks, they really suit local agentic workflows incredibly well. Then there's the speed problem. API rate limits throttle concurrent agents. Locally, there are no rate limits, no queue, no waiting. 8 agents hitting the same local server, 71 tokens per second sustained. And privacy. All your code, all your business logic, all your data stays on your machine. No terms of service changes, no data retention policies. You own the model, you own the output, and you keep your data privacy. So you might be wondering, what model am I actually running? Well, it's called GLM 4.7 Flash REAP. So the REAP version is something you might find interesting. GLM 4.7 Flash is an open source model from GPU AI. REAP is a distillation technique by a company named Cerberus, where knowledge is distilled from a much larger model into a smaller one. It has 23 billion parameters in total, but only 3 billion are active per token. That's the mixture of experts MOE architecture, and it's MIT licensed, so commercial use is allowed. So you might be wondering, why did I pick this model? So I compared a few dozen different models. I was checking things like performance on various benchmarks, how much context I could fit locally on my graphics card, and I quickly noticed that MOE architectures give you fast inference with big model quality, and you generally can have much smaller, more compressed models with the same result as a larger model. It has 200,000 token context window. It has one of the most interesting things is I was able to fit a 200,000 token context window on this model locally. So it can hold an entire code base in context with room to spare. And it was trained for tool use and function calling out of the box. On my dual RDX 3090s with Q8 quantization, it runs 71 to 73 tokens per second. And because it's MOE with only 3 billion active parameters, the full Q8 model fits in VRAM without needing turbo quant or aggressive quantization. No quality loss from compression. So you're running the model at near full precision. What about the economics? So here's where it gets interesting. 71 tokens per second means roughly 6 million output tokens per day. That's approximately $1,200 per day worth of cloud API calls. And the running costs, electricity only. So this is a $2,000 GPU setup. That's $1,000 each, doing the work of a $36,000 per month API build. So let me walk you through how this actually works. Each agent is a Python process with its own conversation memory. All agents share one LLM server. That's Llama server from llama.cpp. They communicate via a central comm server where agents can message each other and me. And there's a lock system that prevents agents from colliding on the LLM. And even more importantly, I'm able to access the setup of the communication, so the chats with the agents, not only from my desktop, but I could access it from my laptop, from my phone. I've got Tailscale set up, so I'm VPNing into my AI rig machine, and I'm able to chat directly with all 8 of my local agents and also with Claude. So here are the 8 agents. I got a PM agent managing sprints, assigning tasks, tracking progress, and detecting stalls in any of the workflows or sprints. The tester agent runs test suites, files bug reports, and validates fixes. The security agent scans for vulnerabilities and checks dependencies. And the ops agent monitors the health of the server, deployment, and infrastructure. So there's a media agent also handling YouTube uploads and subtitle generation. An analytics agent tracking the performance metrics and generating reports. There's a marketing agent that handles content scheduling and social media coordination, and a creative agent that does thumbnail generation and brand consistency checks. So if you were able to listen through all of that, then you might be able to get through the next section where I'm going to talk about the key engineering decisions that made me go with the current processes that I'm using. So a few engineering decisions that made this work. First, conversation memory with compression. Agents remember context across tasks and compress at 70% of the 200K window, so they never run out of context. The second, tool result follow-up. When a tool call returns data, a second LLM call synthesizes the answer. This prevents the classic problem of the agent reading a file, but then forgetting to actually answer the question. Thirdly, a staggered startup. So I have a 3-second delay between agents to avoid lock contention on the LLM. And fourth, stall detection. So what I notice is every so often there would be some kind of bug where a test script would just get jammed or crash for whatever reason. So I have a cron job that runs every 5 minutes, kills hung processes, and just restarts the agent so the loop can continue on in a healthy manner. So because agents will get stuck, you will need automated recovery. And one more thing that I want to mention is, as a an experienced IT professional and computer scientist, over the years, I've noticed that it's very, very difficult to build something that's going to be absolutely foolproof. Um, and you know, it's kind of almost like a point of pride where you might think like, oh, everything needs to be perfect all the time when it comes to software or tech. But the reality is that's almost never going to be the case, especially as a solo developer. So sometimes you just need to, you need to add layers, right? You can't always have something that's going to be perfect, but you can manage your way towards perfection and you still get the result at the end of the day. So my agentic AI swarm was able to run for hours continuously, managing real software sprints. The PM agent autonomously assigns tasks, tracks completion, and escalates blockers. The tester agent found real bugs in the codebase and filed reports. These aren't toy demos, they're doing real work on a real product. And that's the product that I'm developing. So here's what you need to build this yourself. Hardware. Any modern GPU with 16 gigabytes or more of VRAM, but your context window is going to suffer if you don't, boost it up to 24 gigs like the RDX 3090. Dual GPUs. So again, if you want to boost up your context window or run bigger models, you can have my setup where I got dual RDX 3090s, which is really good for running multiple agents with very large context. So, you know, you don't have to need that much power, especially now as models are getting more and more efficient. I've heard Gemma 4 is an incredible model, and I'm going to be planning to actually do some benchmarks and compare it to GLM 4.7 in the future. So that might be a future video. As for software, you've got llama.cpp, which is free, Python, free. There's a communication layer, that's all scripting. You've got the model itself, GLM 4.7 Flash REAP, which is again a free model. The GGUF you can download from Hugging Face. The stack is simple. Llama server serves the model with an OpenAI compatible API. Agent scripts are Python with HTTPX for LLM calls, tool definitions, and conversation memory. And a comms server handles inter-agent messaging. I built mine in Bun and Hono, but any web server works. I mean, it doesn't even need to be a web server. It could be another technology stack, but you just need to have some kind of communication stack in there. So some tips for running this in production. Start with one agent and make sure that it becomes reliable, test it, rework it, improve it. And then when it gets to a reliable point and it's stable, then you add more agents. So also tool definitions matter more than the system prompt. You need to make sure that you have good tools because you could have really powerful agents, but if they do not have good tool call capabilities, they're going to be dumb. So the agents, at the end of the day, they're only as smart as the tool calls and the system prompts that you give it. So always, as well, always make sure to add a self-reflection tool. So this is like almost like a system prompt where you're instructing it to self-reflect on its decision making. And the reason I like to make this a tool call is because you're teaching the LLM to use tool calls for everything. So why not give it almost like a system prompt that it can get from a tool call, if that makes sense. So it will let the agent diagnose its own failures across categories like tools, context, decision quality, and communication. Another thing you might want to do is have some kind of locking mechanism where an agent will be able to lock out LLM access while it's working, because concurrent agents will corrupt each other's generations without this locking mechanism in place. And then you want to add a stall detector, which I talked about earlier, otherwise your agents will get stuck. So you need some kind of automated recovery process, and that's relatively easy to build in, as you proceed and improve upon your agentic AI system. So now here's where it gets interesting. Google just dropped Gemma 4, an open model with some insane benchmark numbers. Agentic tool use jumped from 6.6% to 86.4% generation over generation. So that's a huge increase. Codeforce's ELO went from 110 to 2,150. Math reasoning jumped from 20 to 89%, and it's Apache 2.0 licensed, fully open. The question is, can Gemma 4 run the same 8-agent swarm better than GLM 4.7? So this is a question that I'm going to try to answer in another video. Does the agentic benchmark improvement translate to real-world multi-agent work? I'm benchmarking it right now, but the results will not be available for a while. So subscribe if you want to see the results, because if Gemma 4 delivers on these numbers, it could be a game changer for local AI agents, and it could be the next SOTA model for running agents locally, which I feel GLM 4.7 already was up until recently. So local AI agents aren't a future thing. They're working right now on consumer hardware, doing real tasks. They're improving, and the models are good enough. The tooling exists, and the cost advantage over cloud APIs is massive and increasing. So one more thing I want to say about the cost advantage. Even though cloud APIs are, of course, incredibly cheap right now, you will find that as the subsidies subside, cloud AI, cloud LLMs are gonna start becoming increasingly more expensive, and local LLMs are gonna become more useful not only for orchestration, but even for just coding, or creating your stuff. If you found this useful, like and subscribe.